Oh, hi there. EMC, right? Let me show you something. Today in Solid-state NMR, I'm gonna share with you the story on how we went from the static spectrum of histidine, which is just a block covering the whole spectral width, to this mysterious spectrum who shows some distinguishable peaks. Magic angle spinning is not enough to obtain it, but magic angle spinning alone already improves a lot the resolution solid-state NMR by averaging out the homonuclear dipolar interaction in first order, and faster MAS rates will produce narrower line widths. However, these line widths are still 2 orders of magnitude larger than in the liquid case. To understand the origin of this residual broadening, we've been doing some average Hamiltonian theory analysis, and we found out that both the residual shift and the residual coupling term survive in third order. So we set up the hypothesis that the line shapes here obtained are still limited by residual splitting. We showed in the past that we are able to get rid of this residual coupling by using the 2D correlation experiment Anti-z COSY. Unlike its homolog ZQF COSY, it uses low flip angle pulses, and these ones select correlations only between remote transitions. And this is more clear if we look at the 2D simulated spectrum for both experiments, and we see that with Anti-z COSY we select only the anti-diagonal peaks, and from this 2D we can extract the 45-degree projection, and this will give us the 1D proton spectrum free of the residual coupling. And this is the mysterious spectrum that I showed you at the beginning, which is a projection from an Anti-z COSY at 5 degrees spinning at 100 kHz in a 1.2 GHz magnet, courtesy of Professor Barnes at ETH in Zurich. The resolution improvement is visible for all of the peaks, particularly here in the middle region of the spectrum. And if we look at the individual line widths, for some of them, the resolution improvement factor is over 2. Nice results, but Anti-z COSY needs high resolution in both dimensions, and it actually took us 5 hours to get this spectrum. And we don't got time for that, so how to make it faster? We realized that if we could have in our 2D dataset the shift evolving alone along T2 and the coupling evolving alone along T1, we could reduce the experimental time by undersampling T1 and still get the 1D proton decoupled spectrum. Therefore, we modified the beta sequence and called it TAZ COSY. And after acquisition, we are able to get the shift evolving separately from the coupling with a double shearing transformation. I let you come to me for more details during the EMC poster session, but the main idea to keep here is that we are able to get the 1D proton decoupled spectrum with the same spectral width as in Anti-z COSY, but we only need to acquire a handful of T1 points. And this is the final result that I wanted to show you, where we compare the line widths between the projections obtained with Anti-z COSY and TAZ COSY. And the TAZ COSY projection line widths are within the same range as in Anti-z COSY, and even for some of the peaks they present narrower line widths. But the nicest thing about this spectrum is that we obtained it only in 20 minutes. 20 minutes. Thank you for listening, and allow me to acknowledge all my colleagues. Thank you.